Alright, welcome back. Today we're going to be doing some velocity versus time graphs as opposed to the displacement versus time graphs which we just finished up the other day. Look at that motion. So when we look at a velocity versus time graph, typically you're going to have a zero velocity in the middle of the y-axis here, and then you're going to have a positive region and then a negative region. And then you're going to have time along the x-axis. Now, these have to be read completely different from the displacement versus time graphs. If I give you a graph and it looks the same, but one is displacement and one's velocity, they're going to be describing completely different motions. For example, if I saw a flat line and if it was a displacement versus time graph, it would mean that the object is moving. If we look at this flat line on my velocity versus time graph, what it shows is that we're moving at a constant 11 or 12 meters per second, let's say 12 meters per second, moving forward because we're in the positive region. So it means something different here. If this line had been at the zero, that would have meant that it was stationary. Here, we flip down to the blue line and we get into the negatives, and of course, what does the negative mean? It means that we're moving backwards. So what's going on here? Are we moving forwards, backwards, speeding up, slowing down, moving at a constant speed? What do we see? Well, there's two distinct segments here. There's this region right here, which if I were to look at a downward sloping line of a displacement versus time graph, if this was a displacement versus time graph, what that would mean is moving backwards at a constant velocity. That's not what that means in a velocity versus time graph. This line is in the positive region, which means it's moving forward, even though it's sloped down. The slope down towards the zero means that he's slowing. And then when we reach this line here, we don't stop. We're moving at a constant 5 meters per second. So moving forwards and slowing, then moving forwards at a constant velocity. If we extend that line, so we're moving forward, slowing, 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 slowing. Once we cross the axis here, that's when it's stopped. So it stopped for an instant, and then we're moving backwards, getting faster and faster and faster. Okay, so moving forward, slowing down, coming to a stop, and moving backwards, getting faster and faster. It's getting faster because the numbers are getting bigger. It's going from minus 30 to minus 40 to minus 50. So here on this first segment, which way are we moving, forwards or backwards? We're moving backwards because we're in the negative region. What's happening to our speed? Speeding up, slowing down, or moving at a constant? It's slowing down because it's approaching the zero. So this is moving backwards and slowing, and then coming to a stop right here. So if I wanted to figure out the slope of this line here, so let's look at the slope of the velocity versus time graph. We did rise over run on this triangle. So the rise is 10, the run is 40. Now if I take my 10 meters per second minus 0, because it goes to the origin, and 40 minus 0. If I take my 10 meters per second and divide by my 40 meters per second, I get 0.25 meters per second squared. Now we've seen that unit before. What is measured in meters per second squared? That is acceleration. And that is something you need to know. In order to figure out the acceleration, you can figure out the slope of a velocity versus time graph. That didn't come out really smoothly, but the slope of a velocity versus time graph is the acceleration of that object, and that is something you need to know. Notice that the slope is positive and the acceleration would also be positive. In this graph, the acceleration is constant because the slope of the line is constant. And that's really all we're going to be dealing with in this class is constant accelerations. Maybe every once in a while we'll look at the average acceleration if it wasn't, but not going to be a big deal in this class. So in this case, this object is moving forward because it's in the positive region. It's speeding up because that line is getting steeper, well, it's because it's getting higher and higher. In this case, the acceleration is not constant because the slope isn't constant. Like I said, we're not going to deal with that very much. Okay, let's skip that. All right. So the next thing we need to know about a velocity versus time graph is how to figure out the displacement just by looking at the velocity versus time graph. So let's say we want to figure out the displacement between time is equal to 40 seconds and time equals 30 seconds. So what we're going to do is we're going to multiply the average velocity times the time. The average velocity, because the velocity is a constant 15 meters per second, the average is 15 meters per second. So that's the average velocity, 15 meters per second. Okay, notice the height. And that is going to be multiplied by the time, okay, which if you notice that between 40 and 70 is 30 seconds. That gives us the base. So when we multiply that, we'll find that the displacement is equal to, whoops, what would that be, 1,500 meters. And what we really did here was we looked at the area under the curve, or under the line in this case. That's something you also need to know. The area under a velocity versus time graph is the displacement. So two big points with these velocity versus time graphs. The acceleration is equal to the slope, and the displacement is equal to the area underneath. So those are two big major points. If I wanted to figure out the displacement from 0 to 30 seconds of this graph right here, really all I'm doing is I'm looking for the area of the triangle here, base times height times 1/2. So that'd be 30 times 30 times 1/2, which would be 15 times 30, which would be 450 meters. That would be my displacement. Now, if you notice, this displacement versus time graph, velocity versus time graph is a little bit different because it's got a section that dips below the 0 mark into the negative region. If you were to look at the displacement overall for this entire 70 seconds, in this region it's moving forward, we've got positive displacement. In this region we're moving backwards, we have negative displacement. The overall displacement in this case would be negative 300 meters. If you were given something that was a little more complicated and you were asked to find the displacement, really it just becomes a matter of assuming that the lines are straight, just breaking it up into rectangles and squares and triangles, and then figuring out the areas of all these. So it doesn't end up being a big deal. There's another trick. You can use the midpoint. If you've got a straight line here and the little part that sticks out here takes into account the little part that isn't included here. So that's a little trick. You can just use the midpoint. So what do we have going on here? I don't have a, I guess my 0, my origin is right here. So this is a strange velocity versus time graph. It doesn't have the 0 in the middle. But basically we're moving forwards and we are speeding up. What we want to do is, just in terms of variables, and we'll see this several times in physics where we derive something just in terms of variables without numbers. We want to figure out the displacement based on an initial velocity, a final velocity, an initial time, and a final time. So what is the displacement with these 4 variables? We're going to collapse the T1 and T2 into just T to make things easier, of course. So what we need to do is figure out the area of the first box and the area of the triangle, and add those together, and that'll be our displacement. So the area of the rectangle, that's pretty straightforward. So that's the base, which is T2 minus T1, okay, minus V1. I'm sorry, times V1. T2 minus T1 times V1. Now we're going to collapse T2 minus T1 and just call it time, delta T or time. A little bit more work is the triangle. 1/2 base times height. So the base is again just going to be our time, delta T, which is going to be our time. And the height is going to be V2 minus V1. So we've got that. So let's collapse this just into delta T or T. Okay, so now we have to add these together, and that'll be our total height. So displacement equals V1T plus 1/2 T V2 minus V1. Let's do a little bit of algebraic massaging, Okay, so we'll work this down. I'm not going to go through all this. And what we get when we figure this out is that the average velocity, okay, we figure out the displacement over time equals 1/2 times v1 plus v2. And we arrange it in this specific format, v bar equals v1 plus v2 over 2, because it states more or less the obvious. What it tells us is the average velocity is equal to the average of the initial and the final velocities, v1 plus v2 over 2. Okay, and that equals, but v bar still equals delta x over t. Okay, so that's our third big equation here. V bar equals v1 plus v2 over 2. Now, we can only use that equation, okay, that we just figured out, v bar equals v1 plus v2 over t, or over 2, sorry, when we have something that looks like a box and a triangle, which means we can do something like this. We can't do something like this or like this. So we can do something like this. So here we've got a positive velocity and a positive constant acceleration. Here we've got a positive velocity and a constant negative acceleration. The slope is negative, so the acceleration is negative. We can't do this because it doesn't form that rectangle and triangle, and that's because the acceleration isn't constant. So we can only use this equation when the acceleration is constant. And that's kind of the trick with that one. So this little shortcut comes in handy sometimes, and it's only true if the acceleration is constant. This is true no matter what. It's true by definition. It is the definition of average velocity. Okay, so analyzing some of these velocity versus time graph and displacement versus time graphs. Let's skip that one. Okay. How would I find the initial position? And so you're going to be given graphs, and you're going to be expected to find these things about the graph. So what's the initial position? The displacement from 20 to 60 seconds, instantaneous speed at 30 seconds, the average speed from 0 to 40 seconds, and the acceleration. I'm not going to work all the numbers on this. I'm just going to go over what you would do. The initial position. Well, it's right here. This is the y-intercept. I started at 20 meters. And again, this is a displacement versus time graph. The displacement between 20 and 60 meters. Well, I started at the 30 and I ended up at the 50, so that means my displacement was 20 meters. It's just the difference between those two. The instantaneous speed at 30 seconds and the average speed from 0 to 40 seconds. Well, to get the velocity from a displacement versus time graph, remember what we do is we calculate the slope of the line. Okay? The slope of a displacement versus time graph is the velocity. The slope of a velocity versus time graph is the acceleration. And when you guys get to this in physics, this will all make sense for you. Did I say physics and calculus? So if what we're looking at is we have a constant velocity. So my instantaneous speed is going to be the same as my average speed. So that all I have to do is just find the slope of this line, and that's the instantaneous speed and the average speed over the entire time frame. What is the acceleration? Well, the velocity is constant, so that tells me that my acceleration is 0. So that's how you would do that graph. Let's look at a different one. Another displacement versus time graph. What's the initial position? Well, it looks like we start from 0. The displacement between 20 and 60 seconds, so you would look at here, it looks like about 25 and about 62, so about 27 would be the displacement. The instantaneous speed at 50 seconds. The instantaneous speed at 50 seconds, what you would do is you would make a tangent line. So you would use a ruler and a tangent, draw a tangent line, and use that to find the slope. The average speed from 0 to 70 seconds. Well, the average speed, you're going to use average speed equals displacement over time. So over the course of the 70 seconds, my displacement was about 66, and my time was 70, so 66 divided by 70, so is whatever that is. And so what we're doing is we're making a big triangle that follows this shape. The average acceleration from 10 to 90 seconds. What you would need to do is figure out the velocity here, the instantaneous velocity here by finding the tangent of the line, and the instantaneous velocity here by finding the tangent slope, and then use the acceleration equation, v2 minus v1 all over t. That's how you would do that. If there's one like that in the homework, you can skip that because that's really quite a bit of work and we don't really need to do that. Okay, switching to a velocity versus time graph. What's the initial position? The answer is we don't know. We only know how fast it started. We don't know where it started. The displacement from 20 to 60 seconds. Okay, remember to find the displacement, you find the area under the curve. The instantaneous speed at 50 seconds. That we just read off the graph, so that's like 20, 23, 24 meters per second. The average speed from 0 to 70 seconds. Well, there's two ways I could do this. I could figure out the area under the curve and use that to find the velocity or the displacement, and take the displacement divided by time over 70 seconds. Or I could do V2 plus V1 plus V2 divided by 2. So your initial velocity is 40 meters per second, and your final velocity is 18, so add those up and divide by 2. How we would figure out the average acceleration? Well, it's not as big of a deal to figure out the acceleration on a velocity versus time graph. Remember, the acceleration is the slope of the line, so you would figure out the slope of the line from 10 to 90, which would be that. Moving back to a displacement versus time graph. So I've got two more of these. So the initial position, so we're at about 82 meters, it looks like. The displacement from 0 to 80 seconds. We started off at about 82 and went to, looks like we went to about 2. So my displacement, now notice my displacement is going to be negative in this case. Because it's going to be x2 minus x1, so it's about 2 minus 72, so about minus 80. The average speed, that would be the displacement. Look at the displacement and divide by the time. The instantaneous speed at 0 seconds would be the slope of the tangent line at 0 seconds. And the instantaneous speed at 80 seconds would be the slope of the tangent at 80 seconds. And then the acceleration here, again, if you get an acceleration from for a displacement versus time graph, you don't have to do it. But we already have the numbers from what we just did. So, all right. Let's see. Initial position. First thing we need to check is velocity versus time graph. So that's the kind of graph we've got. Initial position, we don't know. Remember, we only know how fast we're starting. We don't know where we're starting. Displacement from 0 to 90 seconds. What you would do is you would figure out the area under the curve. Now, part of this is above the line and above the 0, and part of this is below the 0. This little segment right here is going to be negative, so you're going to end up subtracting it off from the area of this one. The instantaneous speed at 0 seconds. Well, we just read that right off the graph. That's 40. The instantaneous speed at 90 seconds looks like it's pretty close to minus 10 meters per second. And the acceleration from 0 to 90, you would use your V2, which we just read off as minus 10, minus V1, which is 40, divided by T, which is 90. And that is that.